This video is about operations and properties of vectors. As always, begin by reading through the textbook and taking careful notes, but now consider the following highlights for this topic. We'll begin with what's called component form. Component form of a vector is defined as follows. If a vector v is represented in the plane with initial point P, defined by coordinates x1, comma y1, just in the coordinate plane, and terminal point Q, defined by coordinates x2, comma y2, then vector v in component form can be defined as, first of all, instead of using parentheses, we use these kind of like pointed parentheses. I mean, they're not parentheses, they're more like brackets, but they are as follows. So instead of a left parenthesis, you will have a kind of pointed arrow-looking parenthesis on the left side. And then within those, or within that afterward, you'll find, first of all, the horizontal component. So I'm going to note this separately just to kind of get an idea. On the left coordinate, you'll have what's called the horizontal component, comma, and then after that, you'll have the vertical component, and then a closing, you could call maybe an arrow bracket, again, instead of parentheses. So these symbols are notation for this component form of a vector. And what you're seeing in the definition for the horizontal component is x2 minus x1, and then for the vertical component, y2 minus y1. The reason you're seeing subtraction in those is because on a coordinate plane, that would be like the further one minus the closer one. It's the same kind of thing you would see in the distance formula if you're using algebra in that way. It's just representing a length horizontally for something on the coordinate plane for x2 minus x1, or similarly, it may be a vertical height length on a coordinate system for y2 minus y1. Now, I think it's helpful to see an example of how this could show up on a coordinate plane. So the symbols are helpful, but they're, I think, most helpful when you see them in action. So let's do an example briefly here where we sketch a vector v. Now, this one is given as, or in component form. So vector v is given the components 3, comma, negative 5. And we're also given the initial point. So with initial point P given as negative 2, comma 4. Now let's start with graphing the initial point. Remember, this is just a point plotted on the coordinate plane. So we have a little piece of graph paper here, and we're simply going to plot point P, which is 2 left and then 4 up. Again, just using regular coordinate plane kind of plotting or address. So we'll plot that as point P. Nothing too surprising there. But then if vector v has that initial point that we just plotted, and yet the horizontal and vertical components shown, where the horizontal component given first is 3, that means you're going to move 3 units to the right of where point P is for the horizontal component. Now, you can do this by simply hopping 1, 2, 3 spaces on the graph paper to the right, which is exactly what that means. And then if you have a vertical component, in this case negative 5, that means you're going down 5 units from there. So now you'll go 1, 2, 3, 4, 5 units down from where you were horizontally. So we're starting at P, and then with vector v having horizontal component 3, we went 3 to the right, and vertical component negative 5, that means we go down 5. And then after moving in those directions for those distances, we're going to stop and put our terminal point. Now, if we simply connect the starting and terminal points in the direction that they came, starting with P, and then ending up with really an unnamed point, that will create what we now have as vector v. So we've now plotted vector v in our screen, given the starting point and simply the horizontal and vertical components. It's really just a matter of applying what we have known for a while about coordinate plane geometry or plotting with now these new symbols explaining this in the context of vectors. All right, so we'll do more examples coming shortly, but that's the idea of what this component form means and looks like. Now, to continue on with some definitions, the magnitude, by the way, magnitude is something we introduced in the previous topic. It has the notation of absolute value, and it simply means the length of a vector, how long the vector is. So we've already discussed that, but now we're going to apply a little bit more of a geometric formula to it. So the magnitude or length of vector v, given in component form with components a comma b, remember a being the horizontal component, b being the vertical component as described above. This magnitude is given by the notation that looks like absolute value, but now we have a formula for it. It's equal to the square root of a squared plus b squared, where again a is the horizontal component and b is the vertical component of this vector. Now, this actually looks or will look fairly familiar. So let's actually compute the magnitude of vector v that we just drew above in our graph paper, and then see how familiar it actually might be. If you look at the components of this, then let's use the notation. So we want the magnitude of vector v, which is looking like it's an absolute value. And we know the formula to be the square root of the horizontal component. Now, the one that was given in this vector v above had a horizontal component of 3. That's why we went right 3. So we're going to call that 3 squared for a squared, and then plus the vertical component given as b. Well, in that vector above, it was negative 5. So in parentheses, we're going to put negative 5 and then square that. And then we're going to simplify this result. Now let's do so. So in the square root, we'll have 3 squared, which is 9, plus negative 5 in parentheses squared, which is 25. Of course, 9 plus 25 would be 34. And so the square root of 34 would be the magnitude of vector v given above. Now, it might be helpful to recognize what familiar formula do we use for this, or where is this kind of all coming from? Well, I've already mentioned that it's similar to the distance formula in some of its structure, but actually even that formula comes from something else familiar called the Pythagorean theorem. The Pythagorean theorem is probably an old friend to you in geometry. The Pythagorean theorem means that with a right triangle, a squared plus b squared equals c squared, you could say. So if you bring this into the picture, then you really look at the component form of a vector, such as we have above, as having a horizontal component you can call a for the leg, a vertical component you can call b for the leg, and then a hypotenuse, which is the actual vector, which we'll call c. Well, according to the Pythagorean theorem, in that structure, a squared plus b squared equals c squared. And if you're solving for c, which would be the magnitude of the vector, the hypotenuse side of this triangle, this right triangle, then you would take the square root of both sides and end up with c equals square root. Of course, we use the positive version of it if we're using a distance instead of using a plus or minus. We'll say then c equals the square root of the other side, which is simply a squared plus b squared. Well, guess what? That's exactly what this definition or formula for the magnitude of a vector in component form is. That's exactly where it's coming from, just the Pythagorean theorem. Okay, well, speaking of component form of vectors, let's now move on to some other properties of vectors. And you'll find some of these to use some familiar language, but it's fairly symbol heavy, so it can get a little bit daunting to stare at these, but then practicing some of them with some actual examples next, I think will help make more sense of them. So let's talk first about algebraic operations on vectors. And by this, we mean the following. Let's start with vector u being given in component form as having components a1, comma, b1, and then vector v also given in component form having components a2, comma, b2. Remember, the first of those components in any case will be the horizontal, the second one being the vertical. So what it turns out is this. If you have vector u plus vector v, you are adding vectors here. So this is operations with vectors. You simply add the horizontal components together and then the vertical components together. So vector u plus vector v is going to be in component form here. A1 plus A2, again, that's coming as the sum of the two horizontal components from those vectors, comma, B1 plus B2. Again, those vertical components coming from those vectors. And that's exactly what's happening. You're just adding those components together, the result being whatever the sum of this vector is. We talked previously in our previous topic about more of a geometric look at adding vectors, where you're actually just kind of drawing them either by hand or maybe on a little graph paper grid. We did that in that case, more of a geometric picture of addition for vectors, or maybe even subtraction. But now we're talking about the more algebraic or symbolic way of representing these. And secondly, you can subtract vectors. So vector u minus vector v would be, in a similar way, the subtraction of their components. So now it's a1 minus a2, comma, b1 minus b2. Now, as you may be thinking, subtraction is not commutative, which means the order does matter. So if I'm doing vector u minus vector v, notice the order here. So vector u had components a1, b1, and notice that those are coming first in the subtraction order when we do it for the component form. If I'm subtracting vector v, notice that was defined by the a2, b2 components, the subscripts of 2, those come second. So just take note that the order does actually matter, but we're simply following the order provided, right? If it's u minus v, then we put the u component before the v component when we're doing the subtraction. Or thirdly, we can do scalar multiplication, which again we defined and discussed previously, but now we'll write it as follows. So c, where c is some real number scalar, times vector u is going to be simply multiplying each of the components of vector u by c. So in component form, c times vector u is going to be c times a1, comma, c times b1. You're just multiplying each of the components of that vector by this real number c. Next, we'll talk about properties of vectors, beginning with the 0 vector. The 0 vector has components 0, 0, which is probably what we might expect, right? But it's not just the real number 0, it's a 0 vector. So it has no length and no vertical components, or it has them, but they're both 0. So let's talk about these operations. We can begin with what's called vector addition. And in vector addition, as we already kind of demonstrated above, with some of the basic properties we saw, if you have vector u plus vector v, turns out that's equal to vector v plus vector u. Notice I simply switched the order. Now that should look a little familiar. We're used to this property of real numbers, like 2 plus 3 is equal to 3 plus 2. That's called the commutative property. Commutative property. So there is a commutative property of addition in real numbers. Well, it turns out there's a commutative property of addition in vector arithmetic as well. Or similarly, you'll find this familiar. If you have vector u, so here's our second property, you have vector u plus, in parentheses, vector v plus vector w, parentheses being surrounding the v plus w as vectors. Well, it turns out that's equal to if you had vectors u plus v in parentheses and then plus w. Now, if you go back to your maybe algebra or pre-algebra or even arithmetic, you will recognize this as the associative property. So it turns out vector addition is associative, which again, there is associative property of real numbers that may be familiar to you. This is now just using the same kind of language and symbols, but for vectors. Or thirdly, if you had vector u plus the 0 vector, remember we defined the 0 vector above as having just 0 components, 0 for the horizontal, 0 for the vertical. If you have vector u plus the 0 vector, notice it's not a real number 0, it's the 0 vector, then it's equal to just vector u. In other words, adding 0 does nothing to change the vector, which is probably not that surprising. Now, there's a name for this we could give it if you go back to some of the familiar language in arithmetic or algebra. This would be called the identity, or you could say the additive identity. Identity is relevant because you're getting it's getting itself back. If you put vector u plus the 0 vector, you're getting itself back, the vector u. So that's sometimes referred to as the additive identity. You add it, that is the 0 vector, but nothing else changes, nothing changes, you get the u back. Or relatedly, you could say vector u plus negative vector u. So in that case, by the way, negative vector u with a just negative sign in front of it, that'd be like a -1 as a scalar that you'd be multiplying with the components of vector u. So it turns out if you're adding vector u with its negative vector u, the result is the 0 vector. And of course, this would be called the inverse, or the additive inverse. Just to borrow some language from algebra there. You're adding, but you're reverting back to the 0 vector when you result. So this is the additive inverse. The inverse means you go back to nothing, back to the 0 vector. Or secondly, now after talking about vector addition, let's talk about multiplication by a scalar. So to do this, let C and D be real numbers. We're going to use those letters as our scalars here. The following properties are true. If we have C, that is scalar C, real number C, times, and then in parentheses following it, vector u plus vector v, then it turns out that is equal to C times vector u plus C times vector v. In other words, you can distribute a scalar. That's exactly what you're looking at. If you kind of think back to algebra, it's like you're distributing the C to both vectors, the distributive property. Except C is a scalar, a number, a real number, and the u and the v are actual vectors here. So then the result would be, C times u. We know what that means above. To do scalar multiplication, you'd multiply the components of u times c, right? All right, or you can switch some things around here and say that if you had parentheses containing c plus d, two scalars, and you're multiplying those by vector u, then, well, in the same kind of way, you can distribute the vector to those scalars, resulting in c times vector u plus d times vector u. So this would be kind of like distributing a vector as opposed to a scalar, which the first property illustrated. Or thirdly, if you have c times d in parentheses, those being real numbers, and then you're multiplying that by vector u, then it turns out you can multiply c times d times vector u in parentheses, which is the same thing as d times c times u in parentheses. So there's a lot switching around here. The language is almost worse to try to listen to, but you're associating or grouping different pairs of these factors. So you're multiplying c times the product of d times vector u, or you're multiplying d times the product of c times vector u. And again, this would be similar to the associative property. You're associating or grouping just different pairs. Or thirdly, or fourthly rather, we have 1 times vector u. So this would be 1 as a scalar times vector u. Turns out you just get the vector u. And that would make sense. You're multiplying each of its components by 1, which changes nothing, therefore giving you the vector itself. You could call this the multiplicative identity. And then, so again, some of these names are not always commonly used. We more just use the property itself when doing problems with them. Next, we could have 0, the 0 scalar, times vector u, which turns out is the 0 vector. Again, 0 vector is different from the number 0. 0 is a vector having components, 2 components. 0 as a real number or scalar is just the real number 0. Or lastly, if you have c times the zero vector, c being a scalar or real number, you still get the zero vector because, again, you're multiplying c times each of its components, which are 0, but c times 0 is still 0, so you get the 0 vector back. Thirdly, when talking about the length of a vector, we could do the following. If we have the magnitude notation, so this again is like the absolute value symbols, but inside the absolute values we have c times vector u, c being a scalar, then it turns out that's the same thing as taking the absolute value of c, that scalar, and multiplying it by the magnitude of u, that vector. So if you multiply c times vector u and take its magnitude, that's the same as multiplying the absolute value of c times the magnitude of vector u, is what that property is saying. And fourthly, we'll discuss vectors in terms of I and j. Now, this is just a common notation used we want to refer to here. So it's a lowercase I and a lowercase j, typically, that you'll see for those. And the way you can use this kind of notation is this. If you have vector v in component form being a comma b, so horizontal component a, vertical component b, then you can express that vector in this ij form as the following. Vector v would equal a times I plus b times j, where I and j are those horizontal and vertical components. Just a different way of writing vectors, but there's some convenience to it, as you'll see soon in some examples in doing algebra with those letters I and j. All right, let's try some examples now to see if we can put all this to work for us. Our first example says this: express the vector with initial point p, given coordinates -1, -1, and terminal point q, given components -1, +1, in component form. Now remember, component form, this is where you have the kind of arrow brackets or arrow parentheses holding the components horizontal, vertical for the vector. That's what we're looking for here. Now notice it says initial point p and q as the terminal point. We can start, I think, conveniently by labeling those. If we call that initial point p, since it's defined as the initial one, we're going to give that the subscripts of 1. So we'll call that x1, y1 for point p. And for point q, since we know that's the terminal one, we'll just conveniently use the second letter. So we'll call that x2, y2 for point q, where this vector is ending. And if those are the components given, then we know the formula defined above for our component form. We know that in this case, let's see, we don't have a name for the vector. We'll just call it vector v. The component form for the horizontal is going to be x2 minus x1, as we defined above. So that's going to be -1 minus -1. So again, that's just the x2 minus x1 defined by our formula above for the component for the horizontal component for our vector. It's similar to what you, again, might be seeing in the distance formula if you're going back to algebra and reviewing that. Hopefully with some practice that'll become very familiar to you. So then that's the horizontal component of vector v. It's x2 minus x1. The vertical component would be y2 minus y1. Well, for what we have here, that would be 1 for the y2 value minus -1 for the y1 value. I'm just getting these directly from what we've identified above in our points. We just labeled them this way. And then if this, of course, is y2 minus y1, given the formula we have above. So if we simplify this result, what we'll end up with is that vector v equals the horizontal component of -1 plus 1, really that's 0. So we have a vector of 0, comma. The vertical component would be 1 minus -1, otherwise known as 1 plus 1, or 2. So in component form, so in our triangular looking little parentheses there, our pointy parentheses, we have the coordinates or the components 0, 2. That's the component form of vector v given the initial terminal points defined above. We're just simply computing the components by subtracting the difference, or finding the difference between those point values for the initial and terminal points. Our second example says sketch the vector u. So vector u is defined in component form here with components 4, negative 3. So they're defined in our little pointy parentheses there, meaning that, of course, 4 is the horizontal component, negative 3 is the vertical component. And then they give us the initial point for this vector of 4, 3, 4, positive 3. So actually, we did an example of this above. You may go back and recall this. We're going to start by plotting the initial point of 4, 3. That means from the origin, 4 right, 3 up. We'll just put a little point there to represent that's where our initial point would be. It wasn't given a name, so we'll just kind of put a dot there for it. And from that point, so if we're starting there, we want to use or sketch out a vector with the horizontal component 4. That means I can go 4 to the right from my starting point. So 1, 2, 3, 4. And then the vertical component being negative 3 means I go down 3. So 1, 2, 3. We stop where that ends and put our terminal point down. And since we follow the order provided with initial point 4, 3, we know that the vector extends from 4, 3 down to this new point. And that would be vector u. And they just wanted us to sketch it. Now you can tell, since you're on graph paper, or we're on graph paper here, that if you're starting at point 4, 3, and you're using the components 4, negative 3, then you're going to be ending at the point 8, 0. Just geometrically or algebraically, that's what happens in the picture. All they were asking for here was a sketch, but you can see how the math does all kind of fit together and look hopefully familiar with just basic graphing from algebra here. Okay, our next example says to write the vector u given in component form as 1, 4 in terms of I and j. Well, that's what we discussed above. So we can pick out the horizontal component of this vector as 1 and the vertical component as 4 and plug them in order as follows. So vector u in terms of I and j is its horizontal component, which is 1 times I, plus the vertical component, which is 4 times j. So it's really using the same information in a different way. So it's 1i instead of just the 1 in the component form, and it's 4j instead of just the 4 in component form. Which again may make some wonder, like, well, why even do this if it's really representing the same thing but with more characters, or just what's the point? But there is some use to it, as you'll see further on, with some algebra involved in these. All right, moving on to our next example, number 4. It's listed as follows. It says find 2 times vector u, negative 3 times vector v, and 3 times vector u minus 4 times vector v for the following vectors given. So vector u is given as 2, 7. This is in component form with the pointy parentheses looking things. So 2 is the horizontal, 7 is the vertical components. And then, this is supposed to be vector v here for the second one, given as in component form 3, 1. So let's put these together one piece at a time. The first part says to find, or the first item to find is 2 times vector u. So I'm going to write that out, and then using the components form given as 2, 7, if I'm multiplying 2 times vector u, then really I want 2 times those components. So in component form, if you have the vector 2, 7, but I'm doubling it basically by multiplying that vector by 2, then I simply multiply each of its components by 2 as defined above. So this means 2 times 2, which is now 4 for the horizontal component, and 2 times 7, which is 14 for the vertical component. And that result is now a new vector in component form as 2 times vector u. Next was negative 3 times vector v. And vector v given was 3, 1. So we'll write this out as negative 3 times the component form of the vector with 3, 1 as its components. If we multiply each of those components by negative 3, now that's the scalar this time, then we'll get a new vector with components negative 9, negative 3, in order respectively that way, for the new resulting vector of negative 3 times vector v. Again, the original vector v given as 3, 1. And then thirdly, we wanted the expression 3 times vector u minus 4 times vector v. Now, this is a multiple term expression here. You have a subtraction between two vectors that each involve scalar multiplication. So we'll do that in the same kind of way you might expect here. This is 3 times vector u would be 3 times the original vector u given is in component form 2, 7. So we want 3 times that minus 4 times vector v, again, originally given as 3, 1 in component form. If we simply multiply the scalar by each component in each of these cases, we'll end up with 6, 21 for the first vector minus 12, 4 for the second. But then we're, in this case now, after doing the scalar multiplication, subtracting vectors. And as we defined above, you can subtract vectors by just keeping the order specified. So I'm going to subtract the first horizontal component minus the second in that order. So 6 minus 12 will be, of course, negative 6 for the new horizontal component, and then 21 for the first vertical component minus 4 for the second vertical component will give us a 17. So negative 6, 17 is now the component form of all of the arithmetic done with those vectors. And then moving over to part B of this example, so we're still working with the same expressions given, but now we're given a new set of vectors, and this time, instead of being in component form, they're given in I and j form. So for part B, vector u is given as just 2i. Now, let's be clear that that really means vector u is 2i plus 0j. If j doesn't show up, then there must be a 0 scalar in front of it, which amounts to nothing that it's going to add, but it's still good to note that it's there just as a 0. And then vector v is given in the same kind of form as 3i minus 2j. All right, so let's then put these together using the same expressions as specified. So if we want to find 2 times vector u, the first item in the list, then we're going to take vector u, which remember is just given as 2i. Now you could say it's 2i plus 0j as noted, but that 0j will become irrelevant for what we're trying to accomplish here. So really we could just say this is the same thing as 2 times vector u given as 2i. So it's really just 2 times 2i, which you could multiply as 4i. Now, again, you could say plus 0j, but there's really no need to put the 0 in there. You can assume it's 0 if that j is just missing from the expression. It's probably relevant to note here as well that this I we're talking about for these forms of vectors, this is not I as in the imaginary unit for numbers in algebra. This is just I as in a letter commonly chosen to represent the horizontal component of a vector. So it's not imaginary, it's just a letter representing that. Okay, so 2u ends up being 4i using that ij form. Moving on, then we'll have negative 3v, which was our second expression to find. Negative 3v works the same way. You're going to multiply negative 3 times the ij form of vector v. Now that was given as 3i minus 2j. So this turns into just basic algebra. You're going to distribute, in order to multiply, negative 3 times each of those components of this vector v. So you'll have negative 3 times 3i would be just negative 9i. And then negative 3 times negative 2j would be a positive or plus 6j. And that's where we leave it. So that's the final result. Again, it's still in ij form. It's just using basic algebra to do it. And then thirdly, we wanted to compute 3 times vector u minus 4 times vector v. And in the same way, we'll just put this together using the algebra. 3 times vector u is just 2i. So we'll leave that as 3 and then in parentheses 2i. And then we're going to subtract 4 times vector v, which was given, so I'll put it in parentheses as 3i minus 2j. And we're going to simplify this to be 6i, that's 3 times 2i, minus, we're going to distribute the negative 4 to the second vector here. So negative 4 times 3i would be minus 12i. And then negative 4 times negative 2j would be plus 8j. Just doing basic algebraic distribution here. And then we're going to combine like terms to finish. So 6i minus 12i would be a result of negative 6i. And then we have a plus 8j with no like term to combine with that one, so we'll keep it as is. So negative 6i plus 8j is our result using the ij format for this vector arithmetic. All right, let's move on and do one more example in this topic here. We're going to let vector u equal 2i plus j. Okay, so we have vector u given in ij format there. And then vector v is going to be given as 3i minus 2j. And we want to find several expressions related to those vectors. These expressions that we want to find, of course, are mostly in what look like absolute values. Recall that that means the magnitude, and which really means the length. And we have a formula defined above that will help us do that. But sometimes it's easier to see the vectors in component form, so you can spot the a and the b very easily for the formula of magnitude we have above. What I mean is this. You might find it preferable to rewrite vector u. Okay, so it was given as 2i plus j. Well, that's the same thing in component form as 2 comma 1. And then you can easily spot the a and the b, a being the horizontal component and b being the vertical component. That might be preferable, as you'll see, but you don't really have to write it that way. I'm going to write for both of them in component form here. So then vector v, given as 3i minus 2j, that would be in component form 3 comma negative 2. Again, now we can tell easily what the a and the b would be for those, for that vector and those components. Now, if we put these together, we want to find several things. The first one is the magnitude of vector u. So it looks like absolute values, symbols containing vector u. Well, again, we have above a formula for this, which would be the square root of its components squared added up. So in this case, it'd be like 2 squared plus 1 squared, given the components of vector u being 2 comma 1. Now, I'm going to write those even with parentheses just to be super clear, because they could be negative. And if they are, we definitely want to be careful when squaring a negative. It's in parentheses as we're plugging them in here. So it's really the square root of 2 squared is 4 plus 1 squared is 1. So we're looking at the square root of 5 for this value for the length or magnitude of vector u. Now we need to do the same thing for the rest of these as requested here. So the next thing we want to find is the magnitude of vector v, which we'll use the same formula for. Again, it's convenient to look back at the component form. You can easily spot the a and the b from those components and simply plug them in. We know the magnitude or length is the square root of a squared. Well, that'd be 3 squared. Again, I'm putting these in parentheses just to be clear. And this one has a negative value to its components, so it's definitely important to do that. So for vector v, whose components were 3 comma negative 2, we're going to write the magnitude of vector v as the square root of 3 squared plus negative 2 squared. Again, those being in parentheses. This will give us then the square root of 9 plus 4, positive 4 that is, because of the parentheses, which results, of course, in the square root of 13. And then moving on, the next thing requested would be the magnitude of 2 times vector u. Now, I think it's probably useful if we're liking this component form, and I think it's easy to work with. It's probably helpful to specify near the top of our page what 2 times vector u would be in component form. We did this above with some other examples, so it's not something new, but I think just have this easily referable here or accessible. So 2 times vector u would be simply doubling the components of vector u given as 2, 1. So that would be 4, 2 in component form. You're just doubling the components we already have for vector u. Now, the reason it's nice to have that written is because it's easy to grab and plug in where we need it now. And for the next thing we're looking for, which is the magnitude of vector 2 times u, then all we have to do is say the magnitude of vector 2u equals the square root of its horizontal component squared, so that's 4 squared, plus its vertical component squared, which is 2 squared. We're just getting those directly from the component form, which is just staring us in the face. It's easy to have and use that way. So then we'll simplify this to be the square root of 4 squared is 16, 2 squared is 4. So we're looking at the square root of 20, which we should reduce. So remember, 20 is really 4 times 5. If you go back to some algebraic simplification here, this would be 2 times the square root of 5 for the magnitude of 2 times vector u. All right, so looking back up at our list of what we're trying to compute here with these vectors u and v given, we just did 2 times vector u. Next in our list is 1/2 times vector v. That is the magnitude of 1/2 times vector v. So we have that in absolute value symbols, which are really the magnitude symbols in vector land. So I think it'd be likely useful to do what we just did before and write out whatever 1/2 times vector v actually is in its component form before we compute its magnitude. So 1/2 times vector v as a scalar multiplication means you're just multiplying each of its components by 1/2. Well, the original components given for vector v we already found as 3, negative 2. So this means that if I have 3/2, negative 1, if I'm multiplying each of those by 1/2, 1/2 times 3 is 3/2, 1/2 times negative 2 is negative 1, and so that's now the component form of 1/2 times vector v. What I'm trying to find is the magnitude of this. So I want the now magnitude of 1/2 times vector v, but we now have an easy way to write this because we know its components being 3/2, negative 1. So the magnitude is the square root of the horizontal component squared, that's 3/2 in parentheses squared, plus the vertical component squared, so in parentheses, negative 1, and then squared. And all we got to do is simplify this. So of course, 3/2 squared would be 9/4, squaring the 9, or squaring the 3 and the 2 each. And then negative 1 squared, being in parentheses, is positive 1. Of course, we can combine these 9/4 plus 1 with some common denominator work here. 1 is really 4 over 4, and therefore 9/4 plus 4/4 would be 13/4. So we're looking at the square root of 13/4, and we can reduce the square root of 4 in the denominator there to be 2. So this is really just the square root of 13 over 2 as our simplified result. Probably worth noting that you might see this written slightly differently as well, depending on how it's preferred or which textbook is writing it. So square root of 13 over 2 is fine, or 1/2 times the square root of 13 would be equivalent, of course, numerically. Okay, moving on to what's next. We just did the magnitude of 1/2 times vector v. Next, we want to find the magnitude of vector u plus v, that is vector u plus vector v, and then the magnitude of vector u minus vector v, and then the difference of those individual magnitudes, magnitude of u minus magnitude of v. So again, just to kind of create some useful tools for this, I'm going to spread out what we have already. We were specifying across the top of our page the component form of these vectors because it's just easier to work with when computing the magnitude. So I'm going to do the same thing. I'm going to move what we have been doing downward so I can fit a little bit more up here to do the same kind of thing. So if we're trying to find next now the magnitude of vector u plus vector v, then it'd be probably convenient to know what vector u plus vector v is in component form. And of course, to do that, as we specified above, you're simply adding up the components of those vectors. So vector u being 2, 1, vector v being 3, -2. If I add those vectors together, I'm adding the horizontal components, 2 plus 3 to get 5, comma, and then I'm adding the vertical components, 1 plus -2 to get, well, -1. So vector u plus vector v, the sum of those vectors, is a new vector whose components are 5, -1. What I want next is the magnitude of that vector, u plus v, which we just found. So let's write this out now in that form. The magnitude of vector u plus vector v is going to be the square root of the horizontal component. We just found that to be 5 squared plus the vertical component, which we just found to be -1 squared. And if we simplify this, we're looking at the square root of 25 plus 1, which is, of course, the square root of 26, which can't be reduced, so we'll just leave it as that, square root of 26. Looking above, let's see what was next. So we just did the magnitude of vector u plus vector v. Next is the magnitude of vector u minus vector v. So let's figure out what that is before we figure out its magnitude. So we'll see here. Vector u minus vector v using the component form. Remember, the order matters with subtraction for sure. So the horizontal component of vector u minus vector v is going to be subtracting the horizontal component of u minus the horizontal component of v, which would be 2 minus 3, or in other words, -1. The vertical component, in the same way, in order, would be 1 minus -2. Well, if you're subtracting a negative, remember that's really adding it, so it's really 1 plus 2, which is 3. So vector u minus vector v is a new vector known as -1, 3 in component form, which is convenient to use when trying to find the magnitude, because all we have to do is square the sum of those components. So let's go down to the bottom of our page and write this out. We want the magnitude of vector u minus vector v, which is going to be the square root of the sum of those components, the first being -1, as we just found. So I want -1 squared. For the horizontal component, let's see, the vertical component was 3. So then we want plus 3 squared. Again, I'm putting these in parentheses just to protect for negatives. This results then in the square root of 1 plus 9, or in other words, square root of 10, which cannot be reduced, so we'll leave it as that. And let's see, lastly, we wanted to find the magnitude of u minus the magnitude of v. And of course, we have u and v above. Actually, we already have the magnitude of u. We found that first. That was the square root of 5. We also found the magnitude of v, being the square root of 13. So really, we're just going to borrow what we already did. And keeping the order specified, the magnitude of u minus the magnitude of v, that's going to be the square root of 5. Let's write this out. So magnitude of vector u minus the magnitude of vector v is going to be, well, the magnitude of vector u we already found as the square root of 5. That was the first thing we found. The magnitude of vector v was the square root of 13. That was the second thing we had found. And we're trying to find this expression, but we have to keep in mind everything we know about radicals, which is these are not like radicals. Square root of 5 minus square root of 13 cannot be simplified anymore. So we're just going to leave it right there, and that'll be our result.